Lesson 3, f of x, recognizing functions and their families, function families. This is a 2-day lesson. Day 1, warm-up. Identify the domain and range of the relation described by each set of ordered pairs. Write an equation using the variables x and y that could map the domain to the range. Number 1, your domain let's take a breath. Your domain, remember, are your x values. So I have -3, -2, -1, 0, and 1 as my x values. My range, remember, are your y values, -6, -4, -2, 0, and 2. To create an equation, you have to think, what is my domain? What's happening to my domain to give me my output of my range? Am I adding something? Am I multiplying something? Am I taking away? Well, if I look at this 1 and 2 right here, I can multiply the domain by 2 and get the output. That can happen for all the other situations. So my equation would be y equals 2x. Number 2, the domain are my x values, -3, -2, -1, 0, 1, and 2. My range values are 9, 4, 1, 0, 1, and 4. Sometimes you don't even have to list them out again if they repeat. Now to come up with the equation, y equals, what's happening to the x values to give you an input of y? If I look at this 2 and 4, I notice that if I raise this 2 to the second power, it would give me 4. Basically, I'm doubling these numbers. So here I would have x raised to the second power. I could input these values in for x. -3 raised to the second power would be -3 times -3, which give me an output of 9. Number 3, my domain is -3, -2, -1, 0, 1, 2. The range will be 3, 2, 1, 0, -1, -2. Notice the difference between your input and your output. How is it changing? It's changing into its opposite. So here we could have y equals -x. Our learning goals for this lesson. Define a function as a relation that assigns each element of the domain to exactly one element of the range. That is your textbook definition for function. Take a moment and write that down. The domain, write equations using functional notation. Functional notation is referring to f of x, g of x, or maybe even h of x, a combination of two letters. Your input will be on the inside of the parentheses, and your output will be the letters on the outside of the parentheses. We're also going to recognize multiple representations of functions, determine and recognize characteristics of functions, determine and recognize characteristics of function families. A lot of key terms that we're going to discuss. Some of these terms we've already discussed and we'll reiterate. Below, you have sorted graphs by their geographical behaviors. How can you describe the common characteristics of the graphs? So we're going to use those same graphs from lesson 2. Make sure you have those ready. We're also going to be using a graphing calculator. You can download a graphing calculator app Getting started, odd one out. Which of the graphs shown does not belong with the others? Explain your reasoning. Let's look at graph A, graph B, graph C, and graph D. A lot of things could be said here about why they work or why they don't work. All of these except one is a function. The textbook definition was stating that every value in the domain is mapped to one value in the range. Another definition for function is to say the domain does not repeat. Graph A is a function, and we'll go into detail about why. Graph B is a function. Graph C is a function. Graph D is not a function. Here you can think about all these domain values repeating. We can only have one individual domain. A relation can be represented in the following ways. A relation can be an ordered pair. It can be written as an equation. A relation can be written in verbal situations. A mapping. A graph can represent a relation. A table of values can represent a relation. A function, here's our definition for function again. A function is a relation that assigns to each element of the domain exactly one element of the range. Functions can be represented in a number of ways. So here we're going to look at this table. Analyze the relation represented as a table. Is this relation a function? Well, I'm just going to focus in on the domain. The domain is -1, 2, 5, 6, and 7. Every domain is different. So yes, this is a function. Why is it a function? The domain does not repeat. They are all different. They're all unique. If you look at the range side, just for fun, you notice that your -5s repeat. It's okay if the range repeats. It's not okay if the domain repeats. Let's look at the mapping. An easy way to look at the mapping is to break it apart into ordered pairs. Let's write this as an ordered pair. 1 maps to 2. 4 maps to 5. 4 also maps to -5. 2 maps to 0. Notice anything? Well, I hope that you notice that your domain values, your x values, those 4s are repeating. That means we do not have a function. I don't even look at my y values. I'm not concerned with them. I look at my domain. Number 3, we have a verbal situation. The relationship between students in your school and your students' birthday. Yes, this is a function. Each student has one and only one birthday. Each student has one and only birthday. You can write an equation representing a function using function notation. Let's look at a relationship between an equation and function notation. Consider the scenario. U.S. shirts charge $8 per shirt plus a one-time charge of $15 to set up the shirt design. The equation y equals 8x plus 15 can be written to model this situation. The independent variable x represents the number of shirts ordered, and the dependent variable y represents the total cost of the order in dollars. Here they talk about functional notation. So we could rewrite this as f of x equals 8x plus 15. The number or variable inside the parentheses represents your independent. The entire f of x or g of x represents y. The whole thing represents y. This is a function because for each number of shirts ordered independent value, there is exactly one total cost, which is your dependent value associated with it. Because this relationship is a function, you can write y equals 8x plus 15 in functional notation. You've got the name of the function, which is f of x. You have your independent variable, which is y, x. The cost defined by f is a function of x, defined by the number of shirts ordered. You can write a function in a number of different ways. You could write the t-shirt cost as c of s equals 8 times s plus 15, where the cost is defined as c is a function of s, the number of shirts ordered. So you don't have to use f of x. You could define it a different way. Consider the U.S. shirts C of S equals 8S plus 15. What expression in the function represents the domain? The domain is your S value. The range function is C of S. Describe the possible domain and range for this situation. Your domain, you could order 0 shirts. You could order 1 shirt. You could order 2 shirts and keep going. The range, my outcome, if I ordered 0 shirts, I'm still going to have to pay that one-time setup fee of $15. If I buy 1 shirt, then it'll be $8 plus 15, which gives me $23. If I buy 2 shirts, then that's 2 times 8, which is 16, plus the 15 setup fee, which will be $31. And so forth. The vertical line test. If you notice the green lines, they are representing your vertical line. And it's going to help us to determine whether we have a function or not a function. The vertical line test is a visual method used to determine whether a relation represented by a graph is a function. To apply the vertical line test, consider all the vertical lines that can be drawn on the graph of the relation. If any of the vertical lines intersect the graph of the relation at more than one point, then the relation is not a function. These are fabulous examples. You can use your pencil or pen to represent the vertical line tester. Here, this function intersects at one point. If this line moves to the left or to the right, it's still only intersecting at one point. Over here, where it's not a function, this vertical line is intersecting at 2 points. That's representing 2 domains of the same number. That is not a function. The vertical line also applies for discrete and continuous graphs. Let's remember that for discrete graphs, it is that broken, dotted, slashed graph. It's broken. A continuous graph could be a line, a curve, but it is not broken. Continuous, not broken. Discrete, it is broken somehow. Number 6, how can you determine if a relation represented as a set of ordered pairs is a function? Explain your reasoning. A set of ordered pairs represents a function when each x value set maps exactly 1 to the y. Here's an example of a function. I've got 1, 3, -6. They're all different. This is an example of a function. Your domain is different. The domain does not repeat. The x values does not repeat. Number 7, how can you determine if a relation represented as an equation is a function? Explain your reasoning. An equation represents a function when you can solve for y and get only one value for any given x value. Eight, determine which relations represent functions. If the relation is not a function, state why or why not. So if I think about plugging in some values for x, I'm going to get a unique value for my y. So for example, if I created a table, whoops, let's go back. And I think about this function, and I maybe come up with some values for x and y and create a table. And let's say I plug in 1 for x. So 3 to the first power is going to be 3. Let's say I plug in 2, 3 to the second power is going to be 9, and so forth. I'm going to get unique numbers. This is a function. For every house, there is one street address. This is a function. You're not going to have a house with 2 street addresses. This is a function. C. It's easy to look at the table. Just look at the domain. What do you notice? Your zeros are repeating, not a function. Every value in the domain must be different. Mapping. Let's map them out. 2 to 7, 2 to 20. Are you ready to stop? 4 to 9, 6 to 9, 8 to 2. We could have stopped back here because right here my 2's are repeating, not a function. E, look at the domain. -7, -5, 2, 3. You got a function. Every single one of your domain is different. F, we could apply the vertical line test to F since it's the graph. Think about drawing a vertical line or using your vertical lines that are already on the graph. Do you see how they're only intersecting one point at a time? Imagine your pencil going through the graph. This is a function. It passes the vertical line test. Here are 3 graphs from lesson 2. Analyze the 3 graphs Judy grouped together in the previous lesson, graphs D, K, and O. Are the graphs she grouped functions? Explain your conclusion. Think about using the vertical line test. Look at the y-axis for the first one. We could use that as a vertical line test. See how it crosses 2 points? Not a function. Hey, I could put my vertical line test over here. Not a function. Here, I've got lots of points that it repeats. All of these are not a function. They do not pass the vertical line test. Their domains repeat. Use the vertical line test to sort the graphs in the previous lesson into two groups: functions, non-functions. Record your results by writing the letters of each graph in the appropriate column in the table. So you may want to pause this video, find all those graphs, and sort them. One group is for functions, one group is for non-functions. On the function side, you should have graphs A, B, C, E, F, G, H, I, J, L, M, N, P, Q, R, S. And on the non-function side, you should have guessed it, Judy already grouped those out for us. D, K, and O. Those are the only ones that are non-functions. Activity 3.2. We're going to talk about the domain and range of a function. If you've identified the domain and range of a function given its equation, explain how you can identify the domain and range of a function in a verbal statement. The domain are the possible values that make sense as the independent quantities. The range are the possible values that make sense as the dependent quantities. A graph, to explain how to identify the domain is the set of x values represented by the graph. The range is the set of y values represented by the graph. Here you have a diagram of two graphs given the domain and the range of each graph. They've put it into words and also notation. Take a minute to study this. Remember that your domain are your x values, your range are your y values. Consider the graph cards from the previous activity. That include continuous functions. Label each of these cards with the appropriate domain and range. So I want you to pull out the graph cards that are continuous, not discrete. Remember, continuous are not broken. Discrete is broken. I did mine a little different. I wasn't able to pull out the cards to show you, so I just took the first set of cards. Look at graph A. Graph A for the domain are all real numbers. The range is also all real numbers. Graph B is a little different. The domain represents all your x values, but your range are only the values of y that are less than or equal to 2. Graph C is a little similar. Graph C, your domain is all real numbers. Your range is everything greater than or equal to y on your y-axis. Graph D actually is continuous. It's not broken, but its domain is unique. It is from -4 to +4. All your x values lie in between. Your range is from -4 to 4. Those are your y values. Notice the notation that we're using. E is not continuous. This is a discrete graph. Domain is stated separately. -2, -1, 0, 1, and 2. Your range is also stated separately. -8, 1, and 4. Graph F, your domain is all real numbers and your range is all real numbers. Activity 3.3. We're going to save this for day 2.